Transformers work incredibly well, but why they work has often felt like a black box. What if you could open one up and read the wiring like an electrical engineer reads a circuit diagram? That's the core idea behind the circuit's thread in mechanistic interpretability. In this video, we'll dive into the foundational 2021 paper from Anthropic by Elhage and colleagues, which built on Chris Ola's earlier work. We'll cover the residual stream view of computation, the QK and OV circuits within each head, and what 0, 1, and 2-layer attention-only transformers can express. We'll then look at how these heads compose, and finally, induction heads, the first cleanly interpretable circuit discovered. This assumes you're familiar with the standard transformer block, attention, and basic linear algebra. Alright, let's start with the standard view of a transformer, the one you see in textbooks. You have your input tokens, they get embedded, and then they flow up through a stack of identical blocks. Each block contains a multi-head self-attention sublayer, followed by an MLP sublayer. And of course, there are residual connections and layer norms wrapping each of these components. We typically think about this in terms of layers, like a sequential pipeline. Layer 0 processes the input, passes its output to layer 1, and so on up the stack. But this picture, while correct, hides the structure that really matters for interpretability. The sublayers feel monolithic. It's difficult to ask precise questions like, which specific head in layer 5 wrote information that was read by a specific head in layer 10? We need a different lens. So let's reframe this. Instead of layers, let's focus on the residual connection as the primary object. We call this the residual stream. Picture a single vector, x, of shape d_model. This vector is initialized with the token and position embeddings, and it flows all the way from the beginning to the final unembedding layer. At each computational step, every single component, every attention head, and every MLP layer does two things. It reads from the current value of the residual stream, and then it writes its result back to the stream. That plus sign in the residual connection, x equals x plus head output, is not just some glue between layers. It's the central mechanism. It turns the residual stream into a shared communication channel, like a memory bus in a computer. Heads and MLPs don't pass tensors to each other directly. They communicate indirectly by writing to this shared stream for other components to read. This is a fundamental shift in perspective. Let's get more precise about reading and writing. These operations are fundamentally linear. An attention head reads information from the stream by projecting it through its weight matrices, W sub q, W sub k, and W sub v. The set of all possible inputs, a head can meaningfully process its read subspaces, the column space of these input projections. It's a particular slice of the d_model dimensional space. After the head computes its attention-weighted value, it writes the result back to the stream by projecting its output through W sub O. The column space of W sub O is the head's write subspace. So every head has its own preferred read and write subspaces. This is critical. Two heads can communicate only if the read subspace of a downstream head has a non-trivial overlap with the write subspace of an upstream head. Information flows through these overlapping subspaces. This is the geometric structure where circuits are built. This read/write framing leads to an important observation about bandwidth. The dimension of the residual stream, d_model, is logarithmically 768 for a base model up to over 12 for large ones. But it's finite. In each layer, you might have dozens of attention heads, and each one is trying to write its output, which is roughly d_head or 64 dimensions, back into this shared space. Across the entire depth of the model, you have hundreds of components all writing to the same vector. The residual stream is heavily oversubscribed. There isn't enough space for every component to have its own private, orthogonal subspace to write to. This is the seed of a critical concept, superposition, where many different features get represented in the same subspace. We will return to this. For now, the key picture is this: the residual stream is a communication bottleneck, and every component acts as a parallel reader and writer on this shared bus. Alright, let's dive into the core of information movement, the attention head. You know the standard formula. The output is the attention pattern, A, times the input X, projected through W sub V and W sub O. The pattern A is the softmax of X times W sub Q times W sub K transpose times X transpose, scaled by root D underscore head. This four-matrix view is misleading. The key insight is to group them into two meaningful products. First, the query and key matrices combine into one, W underscore QK equals W sub Q times W sub K transpose. Second, the value and output matrices combine into another, W underscore OV equals W sub V times W sub O. Both W underscore QK and W underscore OV are low-rank maps from D underscore model to D underscore model. And here's the crucial claim: an attention head is fully described by these two matrices. The individual matrices are not identifiable. You can't learn about W sub V or W sub O alone, only their product matters. So let's break down these two new objects. First up is the QK circuit, which is responsible for where information moves. The attention score from a source token J to a destination token I is computed by this bilinear form. The logit before softmax is simply X sub I times the matrix W underscore QK times X sub J transpose. So, W underscore QK acts as a learned similarity metric on the residual stream. It takes two vectorsone from the destination position and one from the source position and computes a single scalar score. A high score means the head wants to move information from J to I. The head attends when the projections of these two vectors onto the query and key subspaces align. This is the only way the query and key matrices appear in the computation. There is no independent meaning to W sub Q or W sub K. They are completely coupled through this bilinear form. Next, we have the OV circuit, which is responsible for what information gets moved. Once the QK circuit computes the attention pattern A, the head's output at a destination position I is a weighted sum. It's the sum over all source positions J of the attention score A sub Ij times the source vector X sub J projected by the matrix W underscore OV. So, W underscore OV is a linear map. It takes a vector from a source token's residual stream and transforms it into a new vector. This new vector is then added to the destination token's residual stream. Every piece of information transported by attention is processed through this single matrix. And just like the QK circuit, W underscore OV is the only meaningful object. The individual matrices, W sub V and W sub O, are arbitrary. You can insert any invertible matrix and its inverse between them, and the product W underscore OV remains the same. Putting this all together reveals a beautifully simple structure. An attention head's full operation can be seen as a tensor product. The head's total output is effectively the attention matrix A tensor product W underscore OV applied to the input sequence. What does this mean? The head's operation cleanly separates into two components. The attention matrix A, determined by the QK circuit, is the position mixing component. It decides which tokens talk to each other. The W underscore OV matrix from the OV circuit is the channel mixing component. It decides what information is moved between them. This separation of position and channel mixing is the central insight. Every attention head, no matter how complex its behavior, is just two simple linear operations, QKs and OV circuits glued together by a softmax. This perspective is what enables us to analyze their function. Let's start at the absolute simplest baseline, a zero-layer transformer. This model has no attention, no MLPS, nothing fancy. It consists of only two matrices, an embedding matrix W sub E and an unembedding matrix W sub U. An input token, represented as a one-hot vector X, is first embedded and then immediately unembedded to produce logits. The equation is simple: logits equal X times W sub E times W sub U. The product of W sub E and W sub U forms a single large matrix. This matrix is effectively a bigram table. For each input token, it gives the predicted probability distribution over the very next token. This means the model can only learn marginal next token frequencies. It's the simplest possible language model, a unigram model in disguise. Now let's add one attention layer, but still no MLPS. The architecture becomes slightly more complex, but a clean separation emerges. The final logits are computed by taking the final residual stream state and multiplying by the unembedding matrix, W sub U. This final state is the sum of the initial embedding plus the output of the attention head. When we expand this, we can see two distinct computational paths. Path 1 is the direct path, where the input embedding flows straight through to the unembedding matrix. This is exactly the bigram model from before. Path 2 is the attention path. The input embedding is processed by an attention head, and its output is added to the residual stream before unembedding. Because logits are a linear function of the residual stream, the total logits are exactly the sum of the logits from the direct path and the logits from the attention path. This path-based decomposition is a powerful tool for understanding exactly what a model is computing. So what can this new attention path actually compute? It turns out that a single attention head implements a specific kind of pattern called a skip trigram. A skip trigram is a 3-token pattern. It says, if you see token A somewhere in the past and you are currently at token B, then increase the probability of predicting token C next. The mechanism is direct. The query vector from token B's position looks for a key vector from a past position, say token A's. This is governed by the W_QK matrix. If they match, the head's attention pattern activates. The head then uses its W_OV matrix to write a specific vector into the residual stream at token B's position. This vector, when unembedded, provides a logit boost for token C. For example, a head might learn, if San appeared earlier and the current token is Francisco, then boost the logit for Bay. The entire expressive power of a one-layer, one-head model is precisely the set of skip trigrams it can implement. This skip trigram model gives us an intuition, but can we make it more concrete? Yes, using linear algebra. Consider the full transformation from a source token's embedding to its effect on the output logits via the attention path. This transformation is captured by the matrix product W sub E times W_OV times W sub U. This creates a massive, vocabulary-sized square matrix. The entry at position I, J of this matrix tells you the exact logit boost given to output token J when the head attends to an input token I. We can analyze this matrix using eigen decomposition. The eigenvectors of this matrix represent stable directions of information flow. For example, if an eigenvector is the identity direction and has a large positive eigenvalue, it means the head strongly copies source tokens to the output. We call these copy heads. This is our first concrete circuit analysis. Diagonalize a single matrix, and its eigenvectors directly reveal the head's function. Alright, let's level up to a 2-layer, attention-only transformer. We now have two sets of heads, layer 1 heads and layer 2 heads. Both read from and write to the same central highway, the residual stream. How does information get from an input token to the final logit prediction? We now have 3 distinct paths. First, the direct path, the original embedding is transformed by the unembedding matrix, contributing directly to the logits. Second, the individual head paths. A single head from either layer reads from the stream, computes its output, and writes back. This output then influences the logits. But the third kind is the game-changer, 2-head composition paths. A layer 1 head writes to the residual stream. Then, a downstream layer 2 head reads that output. This is a 2-step computation. It's crucial to understand heads interact only through the residual stream. There are no secret side channels. This composition of 2 heads unlocks computational abilities impossible for any single head alone. It's a qualitative leap in expressive power. When a downstream head, H2, reads the output of an upstream head, H1, what does that mean? The interaction happens through the matrix multiplications inside H2, giving us three distinct flavors of composition. First is Q composition. H1's output is read by H2's query projection, W sub Q. This means H1's output vector helps determine where H2 should attend from. It's like H1 tells H2 from this position look for these kinds of keys. Next, K composition. Here, H1's output is read by H2's key projection, W sub K. This means H1 modifies what a source token looks like to H2. It's as if H1 tells H2, pay attention to tokens with this new property I'm adding. Finally, V composition. H1's output is read by H2's value projection, W sub V. This is the most direct form. H1 computes some information, and H2 directly picks it up and moves it to its destination. H1 tells H2 what information to transport. The full path for K composition involves the product, W sub K of H2 times W sub O of H1. The strength of this interaction is measured by the Frobenius norm of this product matrix. In practice, most head pairs have negligible composition strength. But a few pairs form strong, interpretable circuits. This idea of composition leads to a powerful abstraction, virtual attention heads. A composition path from an upstream head H1 to a downstream head H2 behaves like a new, effective attention head. It doesn't exist in the parameters, but it's a real computational path. Let's consider the math. The full QK circuit for this composed path involves matrices from both heads. The resulting effective attention pattern is, to a first approximation, the product of the two individual attention patterns, a sub 2 times a sub 1. Likewise, the OV circuit, which moves information, is effectively the product of the two individual OV matrices, W underscore OV of H2 times W underscore OV of H1. So, a two-layer transformer acts as if it has its original heads plus these new virtual heads for every meaningful composition. This massively increases the model's expressive capacity. Importantly, virtual heads can implement more complex attention patterns than any single head. For example, a virtual head's attention can depend on information written into the stream by an earlier head, something a layer 1 head can never do. So why does this all matter? What can a two-layer model do that a one-layer model can't? It can route information in complex, content-dependent ways. The classic example is forming an induction head. An induction head's job is to find a previous occurrence of the current token, then attend to the token that came after it. This is key for repeating patterns. A single head cannot do this. It requires composition. A previous token head attends to the token at position t-1. Then, a second head uses K composition with the first. It uses the information from the first head to find all occurrences of that previous token, allowing it to complete the pattern. This is a profound capability. Composition is what allows the model to perform this kind of in-context pattern matching. And this ability is the fundamental substrate of in-context learning, which we'll explore next. All right, let's dive into induction heads. This is arguably the first truly interpretable, non-trivial circuit discovered in transformers. The core idea is simple but powerful. Imagine a sequence like A, B, C, and then much later in the sequence, another A. What should the model predict next? An induction head is a specialized attention head that helps it predict B. It implements a specific, powerful algorithm. First, find a previous occurrence of the current token. Second, look at the very next token that came after it. And third, predict that token. This is a form of in-context copying. It's a foundational building block for in-context learning, allowing the model to complete patterns it has only seen within the current prompt. Induction heads are not some rare theoretical curiosity. They are present in essentially every trained transformer above a couple of layers and a few 100 million parameters. They were discovered through detailed circuits analysis, and they even form in tiny attention-only models. This is what makes them so significant. They are the first cleanly interpretable circuit found in practice that explains an emergent capability. So how do these heads actually work, mechanistically? It's a beautiful two-head, two-layer composition. In an earlier layer, let's call it layer N, you have a previous token head. Its job is simple. At every position in the sequence, it attends to the token immediately before it. Then, its OV circuit copies the identity of that previous token and writes it into the residual stream. So, after this head, the residual stream at position T now contains information identifying the token from position T-1. Now, in a later layer, say layer N+1, we have the induction head itself. From the current token, second it forms a query. This query is looking for a previous position whose key matches. The key at each position is computed from that position's residual stream. And remember, the previous token head has already written token identities into the stream. Specifically, the key for position K+1 is now a function of the token at position K. The induction head's query for a will therefore match the key at the position right after the first A. This is a direct result of K composition. The induction head's key projection effectively reads what the previous token head wrote. Once attention focuses on that position, the OV circuit simply copies its token forward. One of the most fascinating aspects of induction heads is how they form during training. They don't gradually get stronger. Instead, they emerge suddenly, through a sharp phase change. If you plot the model's loss curve against training steps, you can literally see a kink. It's not a smooth, monotonic descent. There's a distinct point where the slope of the loss curve changes abruptly. Analysis shows that before this kink, the model is relying on simpler strategies, like predicting based on bigrams and skip trigrams. It's learning local statistics. Then, at the kink, the two-head induction circuit rapidly forms. After the kink, the model has unlocked a more general capability, in-context learning. This was beautifully demonstrated in the 2022 paper In Context Learning and Induction Heads by Olson and colleagues. This discovery is a landmark. It's one of the clearest, most direct links we've ever found between a specific, interpretable circuit mechanism and the emergence of a general, powerful capability in a neural network. So, what's the big implication? This framework gives us a concrete program for mechanistic interpretability. The promise is profound. If every head is just two matrices and every circuit is a path through heads, you can, in principle, enumerate everything a transformer does. Now, in practice, MLP layers and superposition complicate this clean picture. But even so, this framework gave the field its first reproducible recipe. You factor attention heads into their QK and OV components, look at how they compose across layers, and find specific, understandable circuits. Using this method, researchers have reverse-engineered circuits for indirect object identification, modular addition, induction, and more. This work is what turned mechanistic interpretability from a speculative art into a legitimate, engineering-grade discipline with clear methods and reproducible results. This brings us to the open problems. MLP layers are significantly harder than attention. They are the primary locus of nonlinear feature mixing and, crucially, superposition. Superposition is the observation that one neuron often encodes many distinct features, and one feature is often represented across many neurons. This breaks the clean, one-head, one-job story. Anthropic's main response to this is the sparse autoencoder. The idea is to dictionary learn the true features from a model's activation space. We can then study circuits in this learned feature space, rather than in the messy, superimposed neuron space. This is the frontier today, building feature-level circuits, creating comprehensive attribution graphs, and scaling these techniques to frontier models. The framework is the foundation. The work continues at transformercircuits.pub. All right, that's a wrap. We've traced the residual stream through QK and OV circuits, building up from zero-layer models to two-layer composition and induction heads. For a deeper dive, the key resources are transformercircuits.pub, the original Distill thread, and Olson et al.'s paper on induction heads. Subscribe and comment on what's next: superposition, sparse autoencoders, or attribution graphs. Coming up, we'll explore toy models of superposition.